Hey everybody, Dr. A here, and in this video we are going to be discussing matrix multiplication, and we're going to include a couple of quick examples. So to get started, we need to remember that matrix multiplication is not the same thing as scalar multiplication. So this is not the same thing as multiplying a matrix by a scalar like I talked about in one of my other videos. So that's one of the key things that's important here. Now, the next key thing to keep in mind is when you're multiplying two matrices, let's say you have a matrix A and you're multiplying that by a matrix B, order matters. And when we say order matters, what we're referring to is the fact that in general, matrix multiplication is not commutative. Now, what does commutativity mean? Well, in general, if an operation is commutative, specifically like scalar multiplication is considered commutative. That means like if you say A times B for two real numbers, A and B, that would equal B times A, right? So think about it, 2 times 3 is 6, 3 times 2 also 6. But when multiplying one matrix by another matrix, in this case, matrix A by matrix B, matrix A times matrix B will not equal matrix B times matrix A. So this statement here, matrix multiplication is not commutative, means that if you have a matrix A times matrix B, in general, that is not going to be the same result as matrix B times matrix A. So you need to remember that. That's a very important property you need to remember, okay? Now, the next thing to keep in mind is that the product of two matrices will yield a third matrix, okay? So that means when you multiply two matrices together, you're going to get another matrix that is their product, all right? So let's call that C, for example. So you could say matrix C would be the product of, for example, A times B, okay? Now, here is basically how this works when we multiply matrices together. So for two matrices to be multiplied, the number of columns in the left matrix must equal the number of rows in the right matrix, okay? So, for example, if you have a matrix A that is an n by m and matrix B is, for example, an m by p, then the multiplication I spell that right, multiplication, there you go. Then the multiplication of A times B is allowed. And the way we can recognize that is that the number of columns in what would be the left matrix is equal to the number of rows in the right matrix. So remember, whenever you have the size of a matrix, the first subscript is the number of rows, the second subscript is the number of columns. So we can put is allowed ... since the number of columns in A equals the number of rows in B. So what you can do maybe to visualize this is you can put these two up next to each other with their sizes down in the subscript. So you have A times B, and you can clearly see that the number of columns in A is equal to the number of rows in B. And so just to help yourself visualize it, you can say these are equal. Okay. Now here's what's cool. Their product, whenever you perform this operation, this product will yield another matrix. We just said that a few minutes ago. Will yield another matrix. Let's call it C. What do you think the size of C will become? Well, the size of their product, matrix C, is going to be an N by P, okay? So the size of the product comes from the number of rows in the left matrix and the number of columns in the right matrix. So let's make a little note here. This value right here is the number of rows of A, and then this value right here is the number of columns of B. Okay, so you can again put these next to each other with their subscripts that indicate their sizes, and that'll help you maybe visualize how this is working. Now, in this particular illustration here, let me ask you a question. Maybe pause the video and think about it. Could we perform B times A? Can I do B times A in this little illustration? Pause the video, think about it. The answer is no. Okay, so we'll make a note here. We're going to say note for this particular illustration, BA cannot be computed. And again, here's how you can look at it. You can say B was a size B was a size M by P times A, put them next to each other. A is a size N by M. And again, remember our basic rule, the number of columns in the left matrix when you're multiplying two matrices together must equal the number of rows in the right matrix. So since these two values are not equal to each other, then the product B times A does not exist. Okay, so we'll say BA does not exist, or you could say cannot be computed. Okay, so let's do a quick numerical example. All right, let's say example, and we want to compute the product AB given matrix A is 1, 0, 2, negative 1, 3, 0, and B is 0, 2, negative 3, 5. Okay, so let's write solution and let's see what we can do. A is what size? A has 2 rows and 3 columns. So A is a 2 by 3, and we're going to multiply that by B. What is the size of B? B is a 2 by 2, so we say 2 by 2. And what do we do next? Well, that's it. This cannot be determined, okay, or does not exist. Why? Because, again, the number of columns of A does not equal the number of rows in B. Okay, so let's do this. Let's do another one where we actually can perform this. Another example, okay? Let's use the same matrices. Compute B times A. Again, A is the same matrix. I'm just going to rewrite it here so we can see a little better. 1, 0, 2, negative 1, 3, 0, and B equals 0, 2, negative 3, 5. All right, can we do this now? B is a 2 by 2 times A, which is a 2 by 3. We can do this. Look, why? Because the number of columns in B equals the number of rows in A. And again, the rule is the number of columns in the left matrix must be equal to the number of rows in the right matrix in order for you to perform the multiplication. Now, what do? Well, multiplying, getting the product is actually the easy part, okay? You're just multiplying and adding things together. So watch what I'm going to do here. Watch very carefully. I'm going to say equals. I'm going to rewrite B here, 0, 2, negative 3, 5. And I'm going to put it right up next to A, 1, 0, 2, negative 1, 3, 0. Now, I'm going to say this equals, and I'm going to open up, I'll tell you what, let me move down to the next page here. Equals, I'm going to open up a new big bracket. Now, here's how you actually compute the product. Stay with me here, okay? You may have to rewind this and re-listen to it. You're going to take the entries from the rows of the left matrix and multiply them by the corresponding entries in the columns of the right matrix, okay? And then you're going to add those together. Rewind the video, maybe listen to me say that again. So here's what we do. We're going to say 0 times 1 plus 2 times negative 1. Okay, let's see where that came from. I'm saying this 0 times this 1 plus this 2 times this negative 1. Again, I'm going to multiply corresponding entries between the rows of the left matrix and the columns of the right matrix, and then I'm going to add those corresponding entries together, and that's going to become my new entry of my product matrix, okay? So this number here, which I have not evaluated yet, is going to be the first entry of this product. Okay, we'll evaluate that in a second. Let's do the next couple of them, okay? Let's do row 1 of the left matrix by column 2 of the right matrix. So that would be 0 times 0 plus 2 times 3. Again, I said row 1 of the left matrix by column 2 of the right matrix, okay? And so that's where I said 0 times 0 plus 2 times 3. Now, that all together becomes the row 1, column 2 entry of the product, okay? Stay with me. Let's find this entry here of our product. We're going to say row 1 of the left matrix times column 3 of the right matrix. So what would that be? 0 times 2 plus 2 times 0. Okay, so 0 times 2 plus 2 times 0. Okay, we're not done yet. We got to populate this bottom row here, okay? So how do we do that? Well, again, one at a time. I'm going to say now row 2 of the left matrix times column 1 of the right matrix. And of course, that's going to become my row 2, column 1 entry of my product. So that would be negative 3 times 1 plus 5 times negative 1. Okay, next, row 2 of the left matrix times column 2 of the right matrix. So I'll have negative 3 times 0 plus 5 times 3. And then my last operation, row 2 of the left matrix times column 3 of the right matrix. So that's going to be negative 3 times 2 plus 5 times 0. And all of this together makes our brand new matrix. Now you want to evaluate these, so let's do some arithmetic. This first, the 1, 1 entry becomes, looks like negative 2. The 1, 2 entry looks like it becomes 6. The 1, 3 entry becomes 0. The 2, 1 entry becomes, let's see, what's -3 minus 5, -8. Next we have 15, and last we have -6. So this is our product right here. So the product BA equals this matrix right here. Okay, one more time. I'll try to say it. So this is my answer. I'm going to say it one more time. Maybe try to say it a little bit differently. What you do is you, one by one, you multiply the rows of the left matrix by each of the columns of the right matrix. And then the row and column designations that you're multiplying together become that spot or that entry in your product. So when you multiply row 1 by column 1, that's going to give you the 1, 1 entry of your product. Then you multiply row 1 by column 2, that's going to give you the 1, 2 entry of the product. Row 1 by column 3 gives you the 1, 3 entry of your product. Didn't mean to move that. Row 2, column 1 gives you the 2, 1 entry. Row 2, column 2 gives you the 2, 2 entry. And then row 2 by column 3 gives you the 2, 3 entry. Okay, so as you can see, the size of our product here is what? It's a 2 by 3. Okay, so maybe pause the video, rewind it, listen carefully to these steps. It is kind of tricky and it's a little hard to explain sometimes, especially on a video like this. But again, you're multiplying each row of the left matrix by each column of the right matrix, multiplying corresponding entries, and then you're adding those two products together. Okay, so think about that and rewind the video and rewatch it as many times as you need to best understand this. Thanks for watching.